we discussed, and I know that you had some question about it, so let's speak about it, about practical task number one. So your task is detailedly described in the file that is called practice number one, and also it is available in the Google Classroom, in our Google Classroom, in the part of tasks. Okay, I will not open it now, but it will be this file. So you have the periodical sequence of rectangular pulses with the special parameters that are described in the table number one. And as you can see, these parameters are dependent of the number of your variants. So our NV here is the number of a variant. And this number is different for all of you. And here you can see your name and the corresponding number of variants. So for each of you, the amplitude, period of repetition, and the shift of the rectangular pulses will be different, as well as the duration of this pulse that is indicated by the Greek letter tau. Okay, and what we have to do with this sequence? At first, we need to just to draw the graph of this sequence. So you should put your parameters in the front and in the top, and then just to draw the picture that will be very similar to this picture that you can see in a slide, but please be careful with the parameters. So you should draw this graph with the parameters that corresponds to the number of your variant. This is the first step. Next step, this is a mathematical. You need to find an expression for dn. And how to do this? In order to get an information, we should open the file presentation. That is our first presentation. It is also uploaded to the Google Classroom. And here there is a very similar example number one and slide number 13, where you can see the periodical sequence of rectangular pulses that you have to deal with in your practical work number one. And here already is formula that gives us the value of Fourier coefficients dn. Let's do it more. Dn. It's a coefficient of Fourier series for the value n, where n is the number of harmonics, and from the start, for you don't need to put some concrete value here. You just write n and remain it's like here. And everything that you need is just to write dn equal to, as it is indicated in a red frame, rectangular frame, and then already just to take the final expression that is here in the second red frame. And here in this expression, at first you just have to write down it in this form like here in the slide, and after this you should put everything that you could from the parameters. You know, parameter A, parameter tau, TP, again tau, again tau. So you should put it here, and as a result you will obtain the formula that is dependent on two values, omega and n. Then let's return to our slide. So your task number one, expression for dn, is already done. Second one is expression for module dn and the phase phi. Again, we are going back to the next slide. And here in the next slide, it's slide number 14, and it contains the solution of example 1. Here you can see the equation, analytical expression for the module dn. Here it is. Actually, if you go back to the slide So you can you can note that dn module is everything like a multiplier that is written before exponent here. So we just repeat it here on the next slide, module dn. And again, the expression for module dn, you should rewrite like it is, and then to put your parameters in this expression. And the same will be for the phase shift, phi from omega. Again, if we are going through the previous slide, so everything that we have in the upper index of exponent, except complex unity j, all the rest, we should put it like an expression for the phase shift. So here is the analytical way, but then you just rewrite it in this form and then put your parameter. Here it's only parameter tau. It's a duration of the rectangular pulse that is unique for each number of variant. Okay, so for the calculation, that's it. And for the graphs, for the graphical part of your task number 1, first one is already done because I told you that first task is you just have to draw this graph like a sequence of rectangular pulses with the concrete values, concrete parameters. The second task is dependence of module dn, and here you just take your expression that you already wrote with your parameters, and you can mark them here that here there is a number n, and n is like a counter, it's changing. So your task is to put consequently, step by step, all the values n from -10 till +10, all integer values, and find what will be with the dn. Okay, and in the coordinates module dn, from dn you will put just these discrete values. You can do it like a dependence of module dn here on the vertical axis, but also in the horizontal axis you can put instead just n, you can put n omega, because you don't know omega, you don't know the round frequency. That's why you can put it here, and in such a way it will be no necessary to calculate it. You will just put instead 1 omega, instead 2 omega, instead 3 omega, and so on. So you will obtain these values, you will put it on a graph, and then it will be just your task number 2 in a graphical form. And the same you can do for the dependence of phase shift phi from n for the same range of the n changing from -10 till 10. So you just take this one, phi from omega, and again you draw the coordinate plane. Your vertical axis will correspond to the value of phi, phase shift, and your horizontal axis will correspond to again to n omega. Okay, so all other you are known. So just changing n from -10 till 10, you will obtain the different values of phi, and you will put it on the coordinate plane. That's all. That's everything that you need, and I hope you will do it very quickly and very easy. And then please upload it to Google Classroom for the checking.